The title of my lectures was Tensor Networks for Gauge Theories, but I will first talk really about just tensor networks in general and try to give you some motivation from the quantum many-body point of view. I will try to give you the intuition of why tensor networks are actually very useful if you want to understand quantum many-body physics from the condensed matter point of view. So but it turns out that, of course, quantum many-body physics, whether you do it for condensed matter or high-energy physics, it doesn't matter. It's basically the same quantum many-body problem. And therefore, I will try to give you some examples or illustrate what I'm developing on hand of some interacting quantum field theories or some simple Bloy models of gauge theories that are very well amenable to this language of tensor networks. So what is the main idea of tensor networks is that instead of describing wave functions in the full Hilbert space, that you are much more interested in describing basically how correlations are distributed among a many-body quantum system. And this is actually very much in the line of some visionary talk of Feynman. Feynman was, in one of his famous talks, he really was sketching this idea that if you want to describe or do quantum field theory, it's a bit crazy to have to know the wave function everywhere just to kind of look at local expectations or local kind of two-body correlations. It would be much better to just have an effective local description of what is the effect of all the other kind of the other part of your Hilbert space, of what is the effect of all the other particles on this kind of small region that you're interested in. And this is exactly what tensor networks can do for you. So they give you they give you a description of how correlations with all the other parts of your system can be locally described. And of course, turns out that these degrees of freedom that give you these correlations are, of course, somehow the entanglement degrees of freedom. So that's why this has very much to do with entanglement. Understanding how correlations are distributed is equivalent to understanding how the entanglement is distributed in your tensor network. So in the first chapter of my lectures, I will try to motivate what the problem is about finding ground states of quantum many-body systems, and try to convey that indeed tensor networks come up very, very naturally there. Then I will move on and describe basically the manifold. So what we will be able to do is then introduce these tensor networks and see that they have very nice and very simple descriptions. And it turns out that they form a very interesting manifold in the big Hilbert space. So if you have like this you will kind of be able to form some manifolds, very low dimensional manifolds of a variational type of states that really captures the physics, all the low energy physics of all possible local Hamiltonians. And then you want to do the physics on that manifold. Okay? And that's exactly actually what the fact that you can do this is really the real bread and butter of this whole tensor network community, because it allows you to actually simulate strongly correlated systems that otherwise are very hard to simulate. So we saw this in the last lecture actually. So although Brian did, of course, it was a very nice lecture, but he could only kind of deal with 14 qubits. So it's really this is the difficulty in quantum many-body physics, is that if you want to simulate a big system, the cost of doing this in the full Hilbert space scales exponentially. And it's clear that all the interesting physics is not going, so you don't need to understand this full Hilbert space to understand the low energy physics or the ground states physics. And this is, the fact that this is possible at all is actually related to the fact that all ground states or low energy states in quantum many-body systems with local Hamiltonians will turn out to have very low amounts of entanglement. There's very few entanglement, and then I will try to kind of, that's why you can actually describe them with tensor networks, and then you can do the physics on this manifold, and what you trade is basically somehow a linear kind of system. You get like you have Hamiltonians in an exponentially Hilbert space. Instead of dealing with this, you will have to deal with nonlinear differential equations or nonlinear physics on a very low dimensional space, and that's of course much preferable. That's much easier, okay? Because you have very few variables. But of course, you have to trade the linear kind of Hilbert space for something nonlinear, and this is exactly these kind of equations that you get that describe effective theories. These are the effective theories that you get using these tensor networks, and that you can actually solve on the computer and then use them to variationally find ground states. And at the end of this first lecture, I would like to, I hope I will get there, is to illustrate actually this, these methods with a simple kind of, with one of the simplest gauge theories that you can imagine in 1D, namely the Schwinger model. So you have a Schwinger model, and it's actually a pretty interesting model because it has confinement. It has lots of the features that higher dimensional gauge theories have. And I would like to illustrate indeed that using these ideas of tensor networks, you can really get all the non-perturbative and all the kind of very interesting non-trivial information out of the Schwinger model, such as entanglement features, also like what happens if you put point charges there, how does the entanglement change if you kind of, as a function of the distance between this, and then you will see indeed that somehow you will have screening and somehow the entanglement will change. So all these things are actually very obvious to do once you have this tensor network language. So in the next lecture, and on Saturday, then I would like to go deeper into, delve a bit deeper into the theory of tensor networks and talk about symmetries. So if you so at the end, these tensor networks seem to parameterize very well the manifold of all low energy states. So it means that if you want to classify all possible phases of matter, it's basically enough to look at the properties of these states. And as is very well known in condensed matter physics or statistical physics or any other kind of field that has to do with many-body physics, so symmetries are, of course, the key in understanding all possible phases of matter. So it's actually pretty amazing that it took until Landau in the 30s to really formulate this, that different phases of matter are distinguished by different symmetries, and phase transitions are about symmetry breaking. So, of course, since the 70s and 80s, it's clear that many, many interesting phases of matter actually don't have a very nice or simple local order parameter. So you cannot just look at them and see phase transitions from the point of view of symmetry breaking. Okay, because the symmetry breaking, it's a topological quantum phase transition. The order parameter is completely non-local. And one of the real values, and that's what I would like to talk about tomorrow, of these tensor networks is that actually recover this Landau paradigm. What you will see is that topological quantum phase transitions, such as of course happens in gauge theories, are completely reflected into the symmetries of these entanglement degrees of freedom. So there will be some local tensors that describe your system, and if the symmetry of these tensors changes, that actually goes hand in hand with a phase transition. So although so you don't have local order parameters anymore, instead somehow you have symmetries of some objects that describe the correlations in your system. And I think this is very intriguing and nice, and it really allows you to kind of have a fresh viewpoint on what gauge theories are and what anyons are and how kind of all the elementary excitations and these non-trivial gauge theories apply. And this has to do, so this has been a topic of intense interest in the field of both condensed matter physics and quantum information theory, because systems that have such topological order are actually very useful for using as quantum memories or as quantum error correcting codes, and therefore would be useful for building fault-tolerant quantum computers. And so I'll see how far I will get this, but this is the plan for the next lectures. So please ask as many questions as you want. But so tensor networks. So it's about quantum many-body physics, and as already said, the big problem in quantum many-body physics is that if you have a Hilbert space of many particles, you have this exponential wall. Okay, so you have an exponential Hilbert space. How do you find ground states? So we will be mainly interested about in terms of in ground states. We will not talk about dynamics at all in these lectures, although somehow it will be clear that you can also do that. Yes?
So how is it that tensor networks are useful for high-energy systems to find ground state when there's typically a large amount of entanglement?
Well, so a large amount of entanglement is of course very relative. So if you, even if you look in a one-dimensional, so let's for simplicity look at the one-dimensional CFT. Actually, if you look at the lattice version of this, so we know that the entanglement entropy of a certain region will scale like the logarithm of that region. That's exponentially smaller than actually the size than it could be. If you would take a random state in Hilbert space, you would have like an entropy that scales linearly in the system, in the block size. for a CFT, it's really logarithmic, so that means there's an exponential compression possible. And that's exactly what basic courses or distance networks do. They take advantage of the fact that there's actually exponentially less entanglement than in a random state. That's why you can do physics. That's basically why you can do physics at all. These states, so the ground states are not generic at all. They have very, very special features. There's a very kind of small corner in your full Hilbert space where all the action is going on for ground states. So there's actually two, as I already alluded to this, but there's actually two aspects that from my point of view make tensor networks so extremely interesting. So on the one hand, there's really this theoretical aspect that by studying tensor networks you really get insight into the structure of entanglement, you really get insight into the different phases of matter. You kind of have really ways of starting to classify different phases of matter, and they will kind of be able to convey that indeed the symmetries of the underlying tensors are really allowing you to kind of get to understand non-trivial phases of matter. But the side that makes it really really new, because of course this theoretical part is like you can reform many things that are already out in terms of tensor networks, but that doesn't mean that you really kind of invent new things. The really kind of useful thing of tensor networks is that you can use it as a variational tool without a sign problem. So there's really, if you want to reformulate this problem, you know that basically concept have to be of this class. You can now look at it from the point of view of a variational method. And you can really start solving problems with that don't have a sign problem. This is extremely valuable in the context of, especially in the context of condensed matter physics, where there's some very basic issues about what spin systems of fermionic things are not known, like the phase diagram of the Hilbert model is like one of the most basic things that you can imagine, and it's really hard to simulate this. Because all you do this with the sign problem. And it turns out that actually these tensor networks seem to be ideally suited for doing this. But of course, there's similar problems for in QCD. If you went to like QCD at finite density, you have also a sign problem. There's no hope that you will be able to do this with the also. So this is basically where we hope that this whole thing will go to. So we are really still kind of in the infancy of trying to understand what this high dimensional or 2 and 3 dimensional quantum many polysystems using these tensor networks. But it's clear that there's a hope that within some not so distant future we will be able to tackle really the hard problems like QCD using these methods. Okay, so let's start talking about what kind of problems we want to solve. So as I already said, so the simplest model, and this is basically the model of all problems that people that are interested in formulated systems in ecosystem or care about, this is the Hubbard model. So the Hubbard model is actually a very simple model of sites. So these sites are basically fermionic spins. So these are sites that could, so this could be, for example, electrons in the S band around some molecule that is kind of in a square lattice. So we are talking about, let's say, a square lattice where with the number of sites on every side you can have an electron with spin up, or an electron with spin down, or both of them, or none of them. And the Hamiltonian that we get for such a system is actually particularly simple. You just get some hopping term. So electrons can hop from one side to the other. This is basically these hopping terms are nothing more than the kinetic energy. So we have something like electrons can hop from one side J alpha plus energy omega. So this is basically the kinetic energy, so these electrons can hop. But then the important term is that there's also some kind of interaction. But this interaction is only on site. So these operators AI are just the creation and annihilation operators of an electron on that side. So the Hilbert space of such a system, if you have insides, is actually 4 to the n. If you have insides, you have 4 massive systems per side, because you can have low electrons, one electron will spin up, one electron will spin down, or one electron will spin up and down. This gives you an energy penalty if you have both energy up and down. This is basically the repulsion between them. And this gives you somehow a term that allows you to hop. So this is supposedly somehow a model that would clarify the issue of IDC superconductivity, but even for the simplest model that you can imagine of kind of an interacting system of electrons, people really cannot solve this using any kind of known methods. Because the phase tree doesn't work. If so the U is large, there's no way of doing interpretation really. Multi-couple doesn't work, so it's really very, very hard problem. And so what people are interested in is basically understanding the phase diagram of this model as a function of J, U, the filling factor, because all this component computes with the number of electrons. So in this method we don't have electron computers. So this is really, in this particular case, there's really a fixed number of electrons in the system. So you have basically four parameters. You have J, U, the filling factor, and the temperature. And you would like to figure out what is the phase diagram. If I can vary these parameters, how is the phase diagram changing of this thing? So this is basically what we would like to do and what these tensor networks are made for. They want to answer, would like to answer these questions. So the reason that people typically focus on spins as opposed to electrons is that actually from this model you can easily go to a model of spin halves, maybe something like the Heisenberg model. So we need neighbors. This is nothing more than a spin, than a set of spin 1/2 particles on this square lattice, where you have no qubits instead of electrons. And this is obtained by taking the limit when U becomes very large, such that electrons kind of repel each other a lot, and you're exactly at half filling. But the limit of half filling and U becoming very large, you can easily, using perturbation, you see that this model is actually equivalent. There will be one electron per side, and they will exactly interact via Heisenberg model. Now, what would be, let's say, the ground state of such kind of model of Heisenberg? So what we have is basically an interaction between nearest neighbors that just tells you that you want to get a signal. Because what is the ground state of such a model if you only have two kind of sites, so you have like a system of two qubits? What would be the ground state of this model? It turns out that this is actually the signet. This is for two sites. So but suppose now that we would have like four sites. So that means that actually the ground state of the system, I would like to be in a signet between these two. I would like to be in a signet between these two, but also between these two and these two. And what you see is that you get some kind of a competition. You cannot be in a signet between these two and these two, and also in a signet between this and this. Because somehow there is this notion of monogamy of entanglement. If I'm maximally entangled with one particle, then I cannot be entangled at all anymore with another particle. So what you see is that there's some competition going on between having indeed something that is as close as possible to a signet, but also, of course, because it's notorious translation invariant, you want to recover translation invariance. It's exactly this competition that gives rise to all the interesting physics, but also the hard physics. If you kind of remember in statistical mechanics, it's all whenever you have a competition, that's what gives rise to interesting physics. Like in statistical physics, it's the competition between entropy and energy. So by making the energy minimal, you typically also make the entropy minimal. And it's really you want to make the entropy as large as possible and the energy as low as possible. And it's by changing the strength of these two kind of cases allows you to drive the system into phase transition into different phases and simply breaking. Well, the quantum version of this is really that it has to do with the fact that you deal with non-commuting operators. If you want to, so the Heisenberg, so the term of the Heisenberg model, the Hamiltonian attack between these two does not commute with the term that occurs here. So you cannot both satisfy that you have the ground state of these two and these two. And this competition is exactly what gives rise to all the interesting correlations in the system. And that's what you would like to capture using tensor network. So the key is in some sense indeed this monogamy of entanglement will allow you will have to make a big entangled state. Everything will have to be entangled to make sure that you are in the ground state of the system. Because it's easy to prove that indeed if you have a Hamiltonian with a certain symmetry that there will always exist a ground state, or at least the ground subspace with the same symmetries in this particular case as the translation invariant. So at the end, we are interested in indeed finding ground states of such Hamiltonians of this type. And the big advances or the biggest interest recently in this has really been that once you understand how to solve such Hamiltonians, how to find ground states, is to classify the different phases of that. We would like to understand, and once I find the ground state of such a thing, how does it compare, or how do different, if I change some parameters in my Hamiltonian, like this J or this U, how does it affect? How can I understand the different phases And for this, we typically look at the deep toy Hamiltonians of this kind, like the Heisenberg model, and we assume that these Hamiltonians have a gap. So for having a different phase of matter, you really have to have gap phases. You have a gap, and then you have another kind of space with the gap, and then there's a phase transition between them where the gap closes. So, the really question is this any way of physical approximation that indeed you deal with Hamiltonians that have a gap? What does that mean? Have a global gap? Why does that physically mean that actually my system is a real system for which there's always perturbations will be describable using such a tools? And there has been lots of advances in recent years by people like Matthew Hastings and many other mathematical physicists, where they actually proved that indeed if you have a global gap in a system, that this in some sense implies that any local perturbation of a Hamiltonian will not change the phase of your system. This is a very highly non-trivial statement, because if you have like a system on a ternary limit or a very big lattice, and you allow for any local perturbation, the sum of any local perturbations, the norm of these perturbations is always much larger than the gap in your system. So you would think, well, perturbation 3 has to break down because the norm of my operator that I perturb with is much larger than actually the gap in my system. Nevertheless, because of the locality of these Hamiltonians, it turns out that this is not true. So this, you don't have to. So the norm of this full perturbation is irrelevant. If the norm of the local perturbations is smaller than the gap, then this is enough to stabilize basically your phase. So even any other kind of perturbation, as long as they are local, they will not be able to destroy the phase of your system. That's why it makes sense at all to think about phases of matter. In gap systems, if this would not be the case, of course, there would be no sense, because any tiny perturbation, but the sum of many small perturbations would completely destroy your system, and it would not be stable at all. This particular case, these are really creation operators of fermions. And they auto-compute and everything. This is level. So they are just auto-computation, they auto-compute on well everywhere. They really obey the usual auto-computation relations of fermionic operators. Yes?
What kind of tensor network captures the final temperature state?
Well, the final temperature is actually a bit easy to write down as a tensor network, because there's if you have a local Hamiltonian, you can just say, okay, let me evolve. It's like a temporal field double state. Let me start with the maximum entangled state that can make a zero entanglement, because it has like you start with the set of maximum entangled states like this, and then you evolve with e to the minus beta h, beta over 2 times h on one part of your system. And this would basically be a purification of your total state. And if the temperature is large enough, then we know that we can approximate this with a pretty low depth on the circuit, and that's how these things work. But it's something I will not talk really about final temperature things. I'm more concerned about ground states, which is in some sense harder when you compare atomic infinity, then this is a more complicated problem. Anyway, so at the end, what you get is all these competitions. Okay? So you want to have translation variants, but you want to have maximal correlations. But the really important thing is that the energy of the state only depends on its local reduced density matrices. So if you have a Hamiltonian like this Heisenberg model or this Hubbard model, the energy of that state is completely determined by the local reduced density matrix. That's the nearest neighbor reduced density matrix. You don't have to know any long-range correlations. The only thing you want to do is minimize the local energy. And it turns out that because of this requirement, what you want is basically that the entanglement is concentrated along somehow a border. So if you have a big spin system, a little bit bigger, and we would like to understand some of the correlations between the left and the right-hand side of such a system, we have to assume that this is really going to the thermodynamic limit. Turns out that the entanglement will be concentrated along that border. And that's exactly what, so the locality of the Hamiltonian implies that the states with minimal energy will also be ones that have all the entanglement kind of concentrate along the border there somehow. Because the locality of the Hamiltonian, it doesn't make sense to have entanglement correlation between this one and this one. This will not help you to lower the energy of your system. The only thing that lowers the energy in the system is to have a correlation between this one and this one. what you have to do is if you have a correlation between this one and this one, you also need the same correlation between this one and this one. But anyway, by maximizing or by minimizing the energy with respect to these local theories, it turns out that all the ground states of gas systems seem to obey something that is called an area law. This is the key in trying to understand or to construct the wave functions or tensor networks that will indeed satisfy this rule. So what is this area law? It tells you that if you have a system, this is like I'm not doing the lattice size, but somehow you have a big system, and you look at the entropy of a certain region A with respect to B. Well, we have already had many lectures on entanglement, so this is really the usual definition. It turns out that this entropy of region A, because I have a pure state, a completely pure state, so this is really the entanglement entropy of region A, will always be bounded by C times somehow the size of the boundary between A and B. This is what is called the area law. And of course there might be corrections, like we already said, if you have a critical system, it turns out that this is not really this, there's some kind of logarithmic corrections to this. But these logarithmic corrections are still very, very small. They're still exponentially smaller than if you would take a random state and calculate this entropy. If you take a random state and calculate the entropy of region A, this would really follow a formula. So this is really kind of much smaller. And the fact that we have an area law indeed is exactly related to the fact that all the correlations are really kind of concentrated along this border. There's no real long-range correlations in the system. And this area laws, it turns out that the really useful measure for these area laws in tensor networks turn out to be Rayleigh entropies. These Rayleigh entropies are defined by the log of the trace. It's not the Rayleigh entropies like you're used like. There may be the Rayleigh entropies for alpha smaller than 1. Okay, so normally I think in quantum field, if you talk about Rayleigh entropies, you think about Rayleigh entropies with integer n. Okay, where alpha is like 2, 3, 4. The really relevant ones are actually for these tensor networks are actually the ones where alpha is a real number smaller than 1. What you can see is that these Rayleigh entropies as a function of alpha, if alpha goes to 1, you can use Qubit and indeed recover the usual von entropy. But for alpha, this is a monotonically decreasing function of alpha. So if alpha goes to 0, this is basically the rank of this density matrix. Okay, this is not useful, but for the moment alpha is larger, strictly larger than 1, it turns out that all the spin systems for which we have exact expressions obey an exact strict area law. So this is a much stronger statement than saying that the von Neumann entropy satisfies an area law. Because for alpha smaller than 1, this thing can be much larger. So this thing is much more sensible or sensitive to the tails of your distribution. If you would calculate the eigenvalues of this reduced density matrix, then these Rayleigh entropies are actually much more looking into the tails. So the smaller alpha is the much more weight we give to the tails. And the important thing for these tensor networks is indeed that the Rayleigh entropies satisfy an area law. Because there's examples where von Neumann entropies satisfy an area law, but nevertheless you cannot represent them using tensor networks. Turns out that for the case that we know, indeed, this stronger version of the area law is actually true. So this is for all the exactly smaller models. This is actually true. These Rayleigh entropies for alpha smaller than 1 also satisfy the area law. Yes?
For alpha smaller than 1, the analytic continuation is fine because the value grows.
Yeah, sure. So this is perfectly, this is just take all the eigenvalues of rho, take them to the power alpha, take the trace of it, the log, and divide by alpha minus. Yeah, there's no problem. It's only at alpha equal to 0, of course, that there's a problem. If you have alpha equal to 0, then this is really the rank, and there it makes sense. But because the rank is always kind of satisfying a volume. But for alpha smaller than 1, but it's not as for alpha equal to 1 half or something like that. So this is, so I know that this actually, so I never really understood whether these, whether if you do analytic continuation with the Rayleigh entropies that you calculate using quantum field theory using this replicatic, whether they actually also analytic continue to alpha smaller than 1. So probably they do, but
You get an output for them.
sorry?
For example, half of the space you get an output for this everything.
Yeah, well, but for spin systems, this is actually what we need and what is satisfied. Okay, so given.
Sorry, is it clear to you that the Rayleigh entropy has error also that the the knowing entropy must have the error law.
So I didn't understand. So
You claim that you claim that it's clear that the entropy must have this error law, but does it mean that if alpha bigger than 0, it is the error law, so alpha alpha bigger than 1, it has the error law, so alpha goes to 1, it also has the error law.
yeah, so it's really monotonic decreasing as a function of alpha. So if it's an area law for alpha for some alpha, then it's an area law for all alphas larger than that. But turns out that the Neumann entropy is not sensitive enough to this whole. You can really kind of create tails or probability distributions that satisfy an area law for the Neumann entropy. Nevertheless, they have such huge tails that there's no way you can approximate them. If you would cut anywhere, you would basically have overlap 0 with the full distribution. So the Neumann entropies are typically not sensitive, not good enough for being able to have this fine-grained information that you need. So let's try to construct now states that indeed systematically satisfy an area law, but also have the properties that we expect from ground state. So if you have a ground state, it really should be something, it should really inherit all the symmetries of your monotorium. So it should, for example, be translation invariant, but also, it should be translation invariant and satisfy the area law. And actually, it's not easy at all, if you think about it, how to write down wave function in many body wave functions that are translation invariant. You just start writing down in your Hilbert space what these things are. Well, it's really not so easy. But nevertheless, there is a construction that is very much inspired by something that's called the AKL tables. This is from Atómico, Kennedy, and Verstraete, and they constructed a particular wave function that indeed has these properties. And what these tensor networks or matrix product states or perhaps or layer, so they can all be seen as generalizations of this construction. So what they were interested in writing down a quantum spin chain. So let's kind of restrict for the moment to one-dimensional quantum-body system. So by the way, from the point of view of entanglement, the lower the dimension, the more entanglement there is. So I already talked about this monotony of entanglement. So the reason that strongly correlated systems are typically restricted to one-dimensional systems because it's matter is that in three-dimensional systems, if you have to share entanglements, if you have to have like singlets like this, you have to have 6 singlets basically of a cubic lattice. This means that you can only have very few entanglements with any of them. That means that you will already be very close to some mean field. So entanglement will not play a role. So the higher the dimension, the less important entanglement actually is, because if you have to share entanglement with many, then you can only have very few with any of them. Okay, so that's why in the case in quantum matter, if you're interested in really exotic, strongly correlated systems, you really have to, so 1 and 2 dimensional systems are always the ones that have most entanglement, because there's the least frustration. You have to share your entanglement with the least number of systems. So what is AKLT? They wanted to construct states that have P-level systems that are spin 1. So we're going to construct spin 1 systems. And they had a very smart kind of way of doing this. They say, look, I want to have something that has, that is as close as possible to a singlet, but I want to have an area law and it has to be translation invariant. Let's start by writing down something that is almost translation invariant and almost has kind of good energy. So let's write down these signets. So like in Einstein level, we would just write down a collection of signets between these two, and so on. So what is clear is that the energy here is perfect. The energy for this term is perfect. For this term is perfect. For this term it's horrible. Then they took the step by saying, actually, let's reinterpret. Let's actually try to understand what these particles are kind of, or something like quarks of a bigger system, of an effective spin system. So let's say that if I have these two spin-and-a-half systems here, that the physical Hilbert space, or physically I don't have access to this full Hilbert space. Like if you have like a neutron, you cannot probe somehow the Hilbert, so this is like a spin-and-a-half system. If you look at you can actually interpret this as a spin-and-a-half system, but we know that there's like quarks underlying this. And you cannot access these quarks, this is a much bigger Hilbert space. So this is basically, in their construction they said something similar. You have two spin-and-a-halves, but let's assume that you can only probe a three-dimensional subspace of this four-dimensional system. This consists of a four-dimensional system, but let's put a linear map here that maps this four-level system to a three-level system. This is nothing more than an example of beta I. So we already have very nice introductions to that network, so I'm moving really fast. So this would mean that I have some linear operator that maps these two spins to my physical Hilbert space. You put this operator here, you put this operator here, same one here, same one here, and so forth. And you immediately see that by construction you need to have a translation invariant state that satisfies the area law of a diagonal, because this one actually satisfies this Rayleigh entropy even for alpha equal to 0. Because it's very easy to see that if you would cut the system into pieces, all the correlations between the left and the right are mediated by this one bond. That means that the reduced density matrix of, let's say, the left chain would really, in this particular case, be rank 2. Therefore, it can only have 2 non-zero eigenvalues. Therefore, the Rayleigh entropy is actually bounded by transduction coefficients, so it can only be, let's say, 1 if you have a blur, two bases, two bases. So anyway, so this is, it's very easy once you have this picture to generalize this, to kind of construct now a complete class of wave functions that are causation invariant and satisfy an area law. So what you do is instead of having siglets here, so you would lift this siglet, so you would say this is something like sum I is equal to 1 to d of I. So this is actually a tangled state between these two virtual spins. And then this mapping, this linear map, maps indeed this d-squared dimensional Hilbert space to a small d-dimensional Hilbert space that would be 2-dimensional, 3-dimensional. This is your physical Hilbert space. And this is basically the definition of your matrix Goldilocks state. So this turns out to be the simplest tensor network that you can imagine. It turns out that all gaps phases of mapping 1D have a ground state that is very well approximated using such a construction. Okay, so I will give you more evidence for that, because you can actually really prove this. You can really prove that if I give you a gap spin chain, then it will have an efficient description in terms of such a matrix Goldilocks state, and I will come back later to what that means efficient. Because for efficient, of course, you need to kind of specify, if I want to make a certain error, how does this bond dimension D have to go? So what you see is that indeed this gives you already, if this D is finite, it gives you really an extreme compression of an extremely efficient or compressed way of saying what the wave function is in your full Hilbert space. You only have to specify one tensor. This is AI alpha beta, and then you put the same tensor everywhere, and this is in one-to-one correspondence, let's say, with ground states of general spin Hamiltonians. Just for the sake of when I'm talking to a public that's probably not very used to cinema halves, there is actually, you can easily come up with a continuum version of such matrix Goldilocks states. So you can really take the lattice spacing to 0 and take a nice limit, and it turns out that the continuum limit of such matrix Goldilocks states that are equally useful, that can actually use as variational ansatz directly in the continuum without ever having to worry about lattice parameters. It turns out that this is something like a path-ordered exponential, let's say between minus infinity and plus infinity of some matrix Q of x plus r of x. So I'm kind of doing this now for the simplest case when I would have like one bosonic particle. So I have like one type of bosonic particle, you act with this on the vacuum. And actually these are matrices, this Q and R, they are D by D matrices. Okay, so what happens is actually that you can take the limit of this A alpha beta, you can say that actually there's no particle, this is like the identity plus something very small, and if there's a particle, this is I equal to 1, this is actually something like a matrix R. You take the continuum limit, and you really end up with some many-body wave function that is really a generalization of coherent states. Because coherent states, you would obtain them with this Q and this R are basically just functions. None of these are matrix functions. Q of x and R of x are really functions, matrix functions, but they are still well defined. That's why you need a part of the exponential, otherwise you cannot make sense of an exponential of some matrices, an integral of matrices. But this is, in some sense, the way this is defined. I'm a bit sloppy here. In some sense, I have to take a trace on here, because I have matrices here. So I should get rid of this virtual degrees of freedom, and as you get by actually taking the trace over this D by D space. That's how you can define, in a very easy way, matrix Goldilocks states in the continuum, and indeed we have been using these wave functions as relational wave functions for quantum field theories. Turns out that they have very nice properties. One of the properties is that they have automatic built-in regulator. So it turns out that if you would calculate for any of these wave functions, one particle reduced density matrix in momentum space, you can actually prove that it's always the case like 1 over k to the 4 in this one-dimensional system, and therefore you have an automatic regulator and you will never run into UV problems. Because somehow 1 over k to the 4 with k the momentum is really fast enough to kill also by emergencies. Anyway, I don't really want to go much into this. Besides that, actually, we are very excited about these continuum matrix works here because it really allows you to start using the variational principle immediately in the continuum without ever having to kind of put it on lattice, and there's well-defined regulators. And it seems to kind of define a little bit what people like Feynman always said is that it's completely impossible to use the variational method for field theories because of the UV problem. If you have like something like Fermi C, and you use the variational method, there's always states with infinite negative energy, and the variational method will always try to fill these modes with infinitely negative energy. So the variational method will care much more about the UV physics than the IR physics because there's much more to gain there. Nevertheless, because of the structure of such wave functions, we don't have to care about this, and we can really overcome these difficulties in the variational method. Then this depends on x is just gone. That should not happen with this x. It's not Gaussian because these are matrices. It wouldn't be a coherent state if these were scalars. But because of the fact that Q and R are non matrices, this is actually a highly non-trivial state. Okay, so but once you have this picture, of course, you can immediately generalize it to any dimension. So it's clear that this picture, well, equally holds for any lattice in any dimension, 2 dimensions, 3 dimensions. So how would you draw a state like that in 2 dimensions? Well, you would start, like on the square lattice, you would start with a collection of these maximally entangled states, and put some operator here that maps the Hilbert space of 4 of these spaces to one physical sphere. So again, what you have, and then you just concatenate all these things to each other. So this is basically called projected entangled pair state, for the reasons that it needs to start with entangled pairs and then project this down with this linear maps. And what this perhaps wave function gives you is indeed, again, some very concise parametrization of your full many-body wave function. Maybe in terms of one tensor, this one tensor basically allows you to tell, well, this is this wave function in this many-body space, this exponentially big space. And similarly, but somehow there's much less proven there is that it's expected that many of the interesting states can be indeed very explicitly represented using such things. So these degrees of freedom is alpha, beta, gamma, and delta somehow, or in this particular case alpha, beta. We call this one of the entanglement degrees of freedom. This is where they are responsible for the correlations in the system. We will see that indeed, things like the entanglement spectrum or entanglement Hamiltonians can be completely formulated in terms of these virtual spaces.
Sorry.
Yes?
Are there continuum pairs?
No. There's some obstruction in indeed doing the same obstruction, and we don't really know why. I would be very glad to talk with you about this. But we have tried this, but there are some obstructions to do this naive kind of generalization. It's a good question. Okay, so what is going on here? So we have our full Hilbert space. Okay, so this exponentially large space, and now what we have here is a very low-dimensional space. Let's focus now to the case of one-dimensional systems. So I have a very low-dimensional space of my matrices A, alpha, I, alpha, beta. So this is like a low-dimensional space. So what I have is that there's some kind of mapping from any point in this parameter space now to somehow this very low-dimensional manifold in Hilbert space. So what you have here is really a very low-dimensional manifold. So these matrix part states or these steps, they parameterize an extremely small dimensional manifold in your Hilbert space. You can actually prove that it's a scalar manifold, and there's lots of differential geometric properties that you can prove about this manifold. And actually, you need to understand some of them to be able to kind of come up with interesting algorithms with it. But one interesting thing is actually that this is not unique. There's actually some fiber bundles. So there's many parametrizations that lead to the same physical state. And it turns out that these many different parametrizations that lead to the same physical state will be crucial in understanding or in classifying the different phases of matter. And the reason that you can see this is that if you look at this matrix product state, it turns out that this matrix product state, if you would write the wave function of this is an easy exercise. You would see that this is basically the sum of I1 to In. Let's assume that we have something like periodic boundary conditions. This would be the trace of A, I1, A, I2, A, In, I1, I2, and so forth. Where the trace is now, of course, over this big D-dimensional Hilbert space. So it's easy to see that actually this is included. That's, of course, why it's called the matrix product state. The wave function, let's say, for a given spin 1, 2, and so on, is equal to the product of these matrices, and then we have to take the trace. That's why it's called the matrix product state. But it's clear that if you have such a representation, you can always put the resolutions of the identity in between. You can always multiply these things with x and x minus 1. But it means that AI and xai, x minus 1, these two parametrizations lead to exactly the same physical state. So there's some gauge, we call them gauge degrees of freedom, and you will see actually that it makes sense later in the lecture why we call them gauge degrees of freedom. But there are some kind of, there's really some degeneracy. So this x, you can multiply this AIs with any matrix x that is invertible, and it will lead to exactly the same state. And the key in understanding, say, issues, but also these different topological phases of matter will be in understanding how these x's will behave when you do some symmetry operations on your physical system. But this will kind of be for later. But that's why, indeed, there's many kinds of states that lead to the same physical state. Okay, so. So once we understood that these matrix product states really make sense, namely they can be used to systematically write down wave functions that have satisfied area of entanglement and organization invariant, we of course started thinking of can we actually prove, can you actually prove that this is the full story? And indeed, if you look at the manifold of all possible low energy states, are they all representable using matrix product states? It turns out that for gap systems, you can indeed ask what is the bond dimension D that I need to be such that the overlap or the difference of my approximated matrix product state with the exact ground state of a certain component with a certain gap, how big does this D have to be such that this is smaller than epsilon? So I want this to be smaller than epsilon, and you ask how does this D have to scale with epsilon such that indeed this is true. What you can prove is that actually D has to be polynomial. I'm assuming that the gap is 1, but of course you can rescale everything with the gap, it goes well with the gap. It turns out that this is enough to take this bond dimension D polynomial in 1 over epsilon and L. Well, L is the size of the system, the number of size that you have in your system. And this is exactly the justification of why this works. Why? So if you will use this as a variational method, you will be able to do things that you cannot do with exact organization, because there's really an exponential compression possible from your full Hilbert space to something that's only polynomial in the system size. So instead of having to work with a vector with exponentially many components, you will be able to deal with a number of components that is a number of variables that is really polynomial. So this is really breaking down the exponential wall. There's a similar question that's actually more interesting for the infinite dimension case. So if you really have an infinite split chain, you could ask how big does the bond dimension have to be to approximate local observables, say local observables of length L. So I want to reproduce all local reduced matrices on L spins. And you ask how big does this bond dimension have to be, and in this particular case, it's actually much stronger. This D has to just to be equal to C over epsilon. This again shows that you have like an incredible efficient description. So in the thermodynamic limit, of course it doesn't make sense anymore to ask about the overlap between two wave functions, because two wave functions are always orthogonal. But if you want to approximate all local reduced density matrices on L size, sorry, this is L, the bond dimension just has to scale linearly in the block size. Yes?
So do the L have to be contiguous?
Yes, it has to be contiguous. But you could of course start proving this also for non-contiguous arguments. But this is like the very simple result. But still, it's in some sense it really justifies the approach. It really justifies that if you use that these weights or these weight exploits, they really capture they really capture the ground states of all cap phases. And again, even if something is critical, it's actually not that bad. Okay, so let me briefly sketch what is going on. If something is critical, so if you want to, so these weight exploits have been used also very much to simulate systems that are actually that are not gapless systems that actually are described by orthogonal theories, orthogonal field theories. And the question is then what happens actually if you approximate such a theory with a finite bond dimension D. And turns out that working with the finite bond dimension D, you do this variation here, find the ground state, is basically equivalent to adding a gap in your system. So this is that therefore you can really use this whole machinery of finite size scaling that Hardy has developed for saying if I want to study a quantum field theory on a finite size or on the lattice, I basically introduce a gap because of the fact that I do it on a finite lattice and then you do the finite scaling analysis. Well, now, with this matrix product states, you can actually repeat this whole construction or this whole idea by saying that D is very much like introducing a correlation like in the system or a gap in the system. And what has been proven by Moore, Polman, and several other people is that indeed working with the finite D for approximating a critical system is like introducing a correlation length in the system that will scale like D to the kappa, where kappa, and this is now for a theory that is described by CFT, it's a very weird number, it's 6 divided by C, with C the central charge times 1 plus the square root of 12 divided by C. Okay, so it turns out that actually using a finite bond dimension D to simulate a critical theory is perfectly okay. You just have to realize that indeed by working with finite D, it's like putting this on a finite size system. You have a gap and a correlation length, and the correlation length is really kind of determined by D to this kappa with kappa equal to this. Of course, in the case of critical systems, there's also completely different tensor networks that you can use, and these are the ones that probably most of you are much more familiar with, and these are these Mera wave functions. These Mera wave functions, they can, well, I'm not good in drawing them at all, but so a very simple way of understanding them is actually only never putting any disentanglements, but only isometries, because this is equivalent. You can always absorb the disentanglements into the isometries. And so what you get is a structure like this, and this indeed. So this is instead of, so in practice actually what people do is this. So you're doing it for a variational method. It's much easier to work with matrix product state than do the finite size scaling and actually applying the variational method on these Mera wave functions. But these Mera wave functions have been introduced by Vidal and of course have very interesting properties from the point of view of insights into the structure of the entanglement. And so what you see is that indeed, so what you have is at every layer you have this scale invariant system with different tensors. So now these are tensors very much like these 3-leg tensors here. In this particular case, it's like a 6-leg tensor. You just stack these things onto each other, and you see that indeed these wave functions seem to capture the fact that indeed the entanglement entropy will scale like a logarithm in the size of a certain block. Because you can put some cuts, your entanglement cut here. I'm not kind of going to redraw this because I'm sure that all of you have seen this many times. But what is very interesting is that indeed this allows you to construct effective Hamiltonians again in the entanglement space. So by looking at somehow this cut and by looking at the wave function defined now on these links, not the original links, but these links, this is exactly again working on an effective space, an effective Hilbert space of the entanglement against field. Yes?
For the bond dimension of the MPS, the gap ground state, can you give intuition on why it would scale polynomially in L, whereas it would seem like that affords you more entanglement than you need?
Well, the proofs of this are actually very hard. Like especially the first thing, they involve, you have to really work with the constant mode, so there's no intuitive way of seeing this. You just really have to do the hardcore things, and this is mainly people like Matthew Hastings that have been doing this, but then they have been improved a lot. To get this result, for example, you really have to, these results of Hastings are not good enough. You really have to use results that computer scientists in the field of quantum information theory have been starting to be interested in these questions like how the approximate ground state is this model in E. So actually, computer scientists have proven that if I give you the promise that my Hamiltonian is gapped, then finding the ground state of that Hamiltonian is actually a problem that is in the complexity class B. You can do it for your time, but the way they do it is really by constructing matrix color states that are the ground states, and they develop lots of interesting tools, and this result is really based on that.
What about the infinite system?
So this is the result for an infinite system here. So this is really about, so the question that makes sense for an infinite system is really, it doesn't make sense to talk about the full wafers. You have to look at this in a C-star algebra point of view. How well can I approximate local reduced answer? Yes?
Wouldn't you expect that they should depend on the gap?
Yeah, sure. This gap is there, but actually I forgot exactly. So it depends on the gap for sure. And if the gap becomes small, then I forgot whether it's actually L. Could it be L divided by the gap? This is kind of, but I actually, it's too long ago that I looked at this. But I think, so of course it depends on the gap, because the gap becomes very small. But again, so even in the gapless case, for a finite system actually, you can prove that D only has to be, so actually even for a CFT, even for a critical system, it's still polynomial actually. So there's nothing diverging. That's why, because if the entanglement entropy is only logarithmic, a polynomial bond dimension will still be able to capture this. So I'm not so sure in the 1D case where this gap is coming. It's coming in a very complicated way, but even if your system becomes, so the gap in a finite, if you have a critical system, and you put it on a finite lattice, then the gap is actually the order of 1 over L. Yes, it's 1 over L, and therefore the bond dimension will actually be polynomial in L. So that's how this enters there. So both the gap is actually, it's never gapless for a finite system. It's always like, it follows from this finite size scaling of R. So it's actually, that's how you get also this polynomial. So this holds both for critical systems and for gap systems. So that's the result. This second result is only for gap systems.
It depends on what system, right? Like, there are these spin chains with what we're calling gaps, but
no, indeed. This is only true for systems that can be described by CFTs. Yeah. So there's this exotic, people have, of course, quantum information theory have tried to construct quantum spin chains whose ground states completely violate area laws. So this is always assuming that I have an area law or some logarithmic correction of the area law. But if once you have a quantum many body system, you can construct them with a gap that is actually extremely small, then you can really come up with examples of ground states that completely violate the area law. And these, of course, cannot be represented using matrix color states.
Is that possible with local Hamiltonians?
Yes, yes. The most extreme case is actually to construct a one-dimensional quantum spin chain whose that is encoding a full quantum computation. So if you can find the ground state of this, you would be able to, so it's a QMA hard problem actually to find the ground state. If you would be able, QMA is the quantum version of NP. So it's completely unfeasible that you would ever be able to find that ground state. So and this is with local Hamiltonians in 1D. But of course the gap of these systems are completely unknown and it's extremely small. And it doesn't fit somehow this whole framework. So I already briefly talked about this, but let me nevertheless stress this notion that once you have this tensor network description, you have an automatic and very natural way of defining entanglement Hamiltonians, or a Hilbert space for the entanglement degrees of freedom. Okay, so this is especially clear in 2 dimensions. If you take this 2-dimensional version of tensor networks like these steps wave functions, you just put tensor everywhere, and of course there's like a physical index everywhere here. And you're interested in understanding the entanglement degrees of freedom, or the entanglement, the entanglement between left and right, so you make a cut somewhere here. So you know that all the correlations have to be mediated by these virtual degrees of freedom. It turns out that indeed the entanglement entropy, so if you look now at, so what you can do is basically cut the right-hand side of the system open and put here the conjugate on top of this. So what you have is your tensor network, you put the conjugate on top of it, but leave these indices open. And what this will give you is basically a density matrix that is defined as a one-dimensional system, and the Hilbert space is defined by this virtual degrees of freedom. Because you put your wave function, you take the overlap with another perhaps, maybe the conjugate of it, but you leave these virtual degrees of freedom open, then this gives you basically a density matrix. And this density matrix, people call it, if you take the logarithm of that density matrix, because it's a positive operator, you get actually the entanglement Hamiltonian. And this entanglement Hamiltonian, the eigenvalues of this entanglement Hamiltonian are in one-to-one correspondence with the Schmidt degrees of freedom, or the Schmidt numbers that you would get if you would cut this system into two pieces. And people in quantum matter physics have been very excited about such entanglement Hamiltonians, because there is indeed, if you do this for quantum Hall systems and things like that, you really get an extremely nice picture. You can relate CFD wave functions to indeed the many-body wave functions in 2D. This is indeed, so what you get is an effective one-dimensional theory that describes, that lives on the virtual degrees of freedom, namely on this edge mode. So equally well, if you have a big system and you want to describe the edge modes, these tensor networks gives you an automatic Hilbert space in which you can describe only 5 minutes. So these virtual degrees of freedom give you an automatic Hilbert space for describing where the edge modes live. And that's a big advantage of working with such tensor networks, because in usual condensed matter systems, it's very hard to see, if people talk about edge modes, where do they live? What is the Hilbert space associated with these edge modes? That's very hard to see, but if you have such a Pep's wave function, then it's clear that indeed, if you leave this virtual degrees of freedom open on the edge, this is basically the Hilbert space for all possible edge modes and edge physics. And as you will see later in these lectures, the symmetries of your tensor network will of course be reflected in the symmetries of these edge degrees of freedom, or these entanglement degrees of freedom, and they will reveal lots of information about in what phase you are. So for example, if these symmetries are non-local, it will mean that indeed the edge physics has to be critical. You would have critical, you will have like a CFT that describes the edge modes. All of this will come out very naturally when you start looking at symmetries of your physical system. Anyway, I don't want to, because I only have 5 minutes, I have to move much faster. So let me briefly give you an idea of how these algorithms actually work. Okay, so how do we actually deal now with these matrix Borg states? So again, so what we have is this manifold of matrix Borg states, and they are described by this parameter space AI alpha beta. So in some sense, if you want to do the physics now, you want to probe the low energy physics of your many body system, instead of working in this exponential Hilbert space that is completely infeasible to do anyway because it's too large, you want to write down basically differential equations here. So if you have the Schrödinger equation, so I times delta over delta t times psi is equal to h times psi, this is just the Schrödinger equation on the many body space. So you would take a point here and then start evolving it with your Schrödinger physics, or your Schrödinger Hamiltonian on that manifold. So what will happen is that this Hamiltonian will typically take you slightly out of the manifold. Because if you start doing, you're not in the grounds anymore, you have low energy physics, there will a slight part of your wave function will kind of take you out of the manifold. But because this is very small, it doesn't cost you, it will not kind of make much difference because this is linear anyway, by projecting this back on the manifold. So what you have is, on every point on the manifold, you have something like a tangent plane. So you can just imagine you have a manifold with a tangent plane. And this h of psi, if you project this back on that manifold, you will have an evolution that stays in the manifold. And if you do this systematically, you just write down this equation, what you will see is that, of course, there's an equation just for AI alpha beta, is just equal to f of a I of beta. So what you get by just doing this carefully, that's actually not very complicated. It's all some simple linear algebra that you have to do. That instead the evolution of your wave function on that manifold can be described by a nonlinear differential equation of just that one tensor. Okay, so this is this extreme compression. Huh? So you have this expansion in our Hilbert space, but now you describe all the physics by just the evolution of one tensor. What is extremely nice is that these equations that emerge from this principle, if you do this carefully, are actually symplectic. So what you get is a symplectic set of systems. So you get a symplectic classical Hamiltonian that describes the evolution of your system. So it preserves energy, it preserves all the possible symmetries. What you get is really a symplectic set of equations that describe the effective evolution of your system on that Hilbert space, but you get really kind of a complete dimensional reduction. Instead of having to work with this quantum spin chain, now you would just work with this one kind of zero-dimensional object. And indeed, this is symplectic. This has this really has Poisson brackets. This has the full kind of picture of a classical system. Yes?
Can you do something similar on Mera and do some other?
Yes, actually, whenever you have something that you have a manifold and you have some nice way of defining projectors on the manifold, then what you do here is called actually the time-dependent variational principle. And whenever you have a nice manifold with some nice features, I don't know whether Mera has these nice features, but I suspect so, then indeed you're guaranteed that the ensuing equations are symplectic actually, and preserve energy and all these properties. But it's really very nice because you get really Poisson brackets, you get an effective classical description of your full quantum many-body system. And that means that because you have now this full, it's not just the static information, you actually have these classical equations, you can start thinking about constructing an effective Hamiltonian that you get by projecting now your full Hamiltonian on that tangent plane. So what you can do to find ground states, and it turns out that all the best algorithms for finding ground states in the variational method, what you do is instead of putting an I here, you just put a minus here. So what you do is evolve your state in imaginary time, then you know that basically you evolve exponentially fast to the ground state if you would do this exactly. But now you put this projective there, find the equivalent equations that ensue here, discretize this, use some splitting methods, all these things. Turns out that all the different algorithms that people have ever come up with to variationally work with matrix product states can be traced back to different ways of splitting these differential equations. So if you have a differential equation where you have with many terms, you have to first evolve this and this. Well, the only thing that people do with the difference in different algorithms is just the different ways of splitting this equation. So this is basically the model equation of all variational optimizations with these tensor networks. And so once you evolve this in imaginary time, you, for example, evolve to this point. And at that point, you're in a stationary point of this differential equation. Then what you have, a very natural object, is now the tangent space on the manifold around that point. You have this stationary point, and then you look at this tangent space around this. There's a very nice linear subspace, and if you project your full Hamiltonian now on that linear subspace, you will have all the information about the low energy physics in your system. So this allows you to probe the excitations, actually the elementary excitations, the elementary particles in your theory. The excitations on top of the system are nothing more than the eigenvectors of this effective Hamiltonian that you get by doing such things. So I think I have to stop here, so let's continue tomorrow. Thanks.
What is the length of time that you're able to evolve for before getting accruing errors that are too large when the time becomes?
Well, if you do it in imaginary time, you don't care about errors because it's a dissipative thing. No? So imaginary time is, if you make an error, this is irrelevant. You will nevertheless. But of course, there's no guarantee that you will actually find the global optimum.
But I'm saying if you do real time.
If you do real time, then this is a big issue, of course. So if you do real time like Brian did in the previous talk, then the entanglement entropy grows linearly in time. That means that the bond dimension has to increase exponentially in time, and therefore you will only be able to do very short time scale. Nevertheless, for these chaotic systems, it should be possible to actually simulate this using this time evolution, but you don't want to really don't want to simulate your pure state evolution. What you have to do is you must have some mechanism that turns quantum entanglement into classical correlations. Because we know that once you thermalized, the thermal state itself can again be efficiently represented using matrix Borg state, but not using pure states, but using mixed states. It's not that this exponential growth of the one dimension should be a problem. There should be a mechanism of reducing it, but we have been looking for this for a long time and never managed to do this. And actually, I talked to quite a few people here at this conference. This problem seems to be equivalent or very related to the problem of if I have a many body state that thermalizes, what are the observables that I have to measure that would correspond to the observables inside the black hole? If you measure these observables, they would not affect the physics at later times, namely the local reduced density matrices, but they would turn pure states into mixed states. And if anybody has an idea, I would be very interested in knowing.
Questions? In the continuing version, suppose you want to use it to say how the ground state of a 5.4 Hamiltonian, what is the difficulty there? So it's very difficult to evaluate the
No, we actually have done it, let's say, for cross neveu. Model. We have not done it for 5 to the 4. We have done it for fermionic system here, Schwinger model. We have done it and it works, just works. Of course, there's some kind of built-in regulator, you have to be careful with. But the regulator is basically the norm of these matrices. If the norm of these matrices is bounded, then you automatically have this regulator. But I showed you that this is 1 over k to the 4 effect, that if you plot the one part can reduce density matrix in momentum space, you're guaranteed for any one of those that this goes down like 1 over k to the 4. And that's safe, so that's why it is possible to simulate, to overcome some of the problems of the... Well, at the end you do exactly the same like this. No? You really kind of construct this CMPS manifold, project on this, you get differential equations, you just solve these differential equations and you find the ground state. So on the ground state you can start probing the excitations. This is of course particularly interesting in the quantum field case, what you have ground states, all this. I wanted to show this actually.